Okay, today we're going to talk about counting problems, and these are going to take a bunch of different forms, so let's dive right in. So we're first going to learn how to solve simple counting problems, and then we'll learn about the fundamental counting principle to solve counting problems and using permutations and combinations to solve counting problems. Now we've introduced combinations, at least in the last video, and permutations are kind of a different take on that as well, so let's get started. So let's talk about the fundamental counting principle. Let's say that you have two different events, and we'll call this event A and event B, and they can occur in two different numbers of ways. So A can occur X different ways, and B can occur Y different ways. The number of ways that the two events can both occur together is going to be X times Y. Now, let's give you an example to help you understand this. So say we have two six-sided die, okay? So we have dice 1 is event A, and dice 2 is event B, right? We want to know what are the number of ways that the two dice could be rolled together, okay? So if I want to roll dice A, I've got 6 different ways that can happen, and if I want to roll dice B, I've got 6 different ways that can happen, right? So total, I've got 36 different ways that I could have the dice roll. I could have a 1 and a 1, a 1 and a 2, a 1 and a 3, 4, 5 and 6, right? And I could have a 2 on the first dice, on the first die, and a 1, 2, 3, 4, 5, 6, right? Okay, so there were 6 ways for the first, 6 for the second, and on and on and on till 6, and so we end up with 36 different ways that we could have those dice be showing numbers on top, okay? So let's talk now about permutations. A permutation of, let's say, n different elements is an ordering of the elements such that one element is first, another one is second, and another one is third, okay? So what we mean with this is that the order of the numbers matters, okay? So we have the number of permutations of n elements is just going to be n factorial, okay? So let's talk about the number of ways we could arrange 4 people into 4 roles of student council. Okay, so say we've got person A, person B, person C, person D, and we've got 4 different roles. Well, if I put in person A as president, then that leaves person B, C, and D, right? So the only people left to fill vice president, okay, are B, C, or D. Now I could have used any of the first 4 people to fill slot A. But by the time slot A is filled, I've only got 3 left for slot B. I've got 2 left for slot C, or for secretary, sorry, and 1 left for treasurer, right? Well, that means that the number of ways I can arrange this is 4 times 3 times 2 times 1. Okay? And why times? Well, because we want to do president and vice president and secretary and treasurer. And if you get into a statistics course, and I highly recommend you take a statistics course to better familiarize yourself with this, you'll find out that when we want to do and type things, that means multiplication or means adding when we're talking probability, okay? So 4 times 3 times 2 times 1, so we have a total of 24 different ways that we could arrange 4 people into those 4 roles. Now let's talk about a little bit different take on this, and this is permutations of those n elements, but we're taking them r amount at a time, okay? So suppose I have 10 people running a race. How many different combinations of people could take the first, second, and third place medal? Well, say I've got first place, and I've got second place, and I've got third place, right? For the first place medal, I'll have 10 people that could have gotten it, right? But after that first person crosses the finish line, there's only 9 people left to go, right? And after that second person crosses the finish line, there's only 8 left to go, right? So this amounts to 10 times 9 times 8, which is 720 different combinations of those people. Well, that's taking 10 people and arranging them 3 at a time, right? For first, second, and third place. So we call this a permutation of n elements taken 3 at a time. So NPR, not the radio, but is going to be n factorial, which was 10 factorial, 10, n was 10, divided by 10 minus 3 factorial, right? So that ends up being 10 factorial divided by 7 factorial, right? Well, if we recognize that 10 factorial is 10 times 9 times 8 times 7 factorial, then dividing out that 7 factorial just leaves me my 10 times 9 times 8. So you can either think of it the way I first explained it, or you can use the formula, because either way you're going to come out with the same result, 720. Now let's talk about distinguishable permutations. So suppose we have a set of objects, and those set of objects has different types or categories in it, and that's supposed to be an H in front of there, has different types or categories of items in it. We have to rework our permutation formula to be able to account for those, okay? So suppose we have the word Mississippi. How many different ways could we order those letters? Well, I've got M's. I've got 1. I's, I've got 1, 2, 3, 4. S's, I've got 4. And P's, I've got 2. Okay? So how many different ways can we order the letters? So how many letters total? We have 3, 6, 9, 10, 11, right? So we have 11 items, and we have 4 different categories. So we're going to have our 11 factorial divided by 1 factorial times 4 factorial times 4 factorial times 2 factorial. So that will be, let's see here. So that will be 39,916,916, I got my numbers backwards, 916,800 divided by 1 factorial is just 1. 4 factorial is 24, so 24 times 24 times 2 factorial, which is 2, so 24 times 24 times 2, and that's going to be, so 39,916,800 divided by 1,152. So we've got 34,650 different ways that we can order the letters in Mississippi. We've got 11 items, and we are going to have them in 4 different categories, right? Now let's say that we know that permutations count different orders of the same item types, okay? So that means that ABC is counted as a different item than ACB, right? Same letters, different order, okay? That happens, that's what we're counting when we count the number of permutations. Now, what happens when you don't care about order? When you want to say, hey, ABC is the same as ACB, I don't really care. As long as I've got an A and a B and a C, I don't care about the order, okay? Well, we call these combinations, okay? And we want to be able to figure out how many things, say my order doesn't matter, that we have, right? Okay? We want to be able to count these types of things, and we call those a combination. So when we're talking about a combination lock, it's really not a combination lock, it's a permutation lock, okay? But that's just a little math joke. Okay, So we call this a combination. We've already introduced this, right? We're taking a number of combinations of n elements taken r at a time. So NCR is n factorial over n minus r factorial times r factorial. Okay? And most of your scientific calculators have buttons for NCR and NPR. Okay? You'll enter a number, you'll hit your NCR button, and then you'll enter another number, and then you'll hit your enter button. So your first number will be your N, then you'll hit your button, then you'll hit your R, then you'll enter your R number, and then you hit enter again to find out the number of combinations, okay? So you have generally a button for each of these, so you don't really have to memorize the formula, you just need to know what it's useful for and how to find it on your calculator. But let's learn about what it's useful for. So say we want to figure out how many different 7-hand combinations we could have, or 7 card combinations in a hand that we could have of a 52 card deck, okay? So that is asking, I've got 52 things, combinations taken 7 at a time, right? And so when we are calculating this, you know, if we've got the cards, we don't really care about the order. That's up to the person who has them in their hand to order them however they wish, right? We just want to have the actual cards. So that will be 52 factorial divided by 52 minus 7 factorial times 7 factorial. Okay? Now, that's an awful lot to enter into a calculator, and so that's why we actually have the buttons for it, because people do this so often. Now, when we are doing this on our Inspire CXs, you're going to hit the menu button, which is the third down on the right, and then you're going to hit 5 for probability, and then you're going to hit 3 for combinations, and you are going to enter 52, and then you're going to hit your comma button and enter 7, slide over to the right and press enter, and you'll get 1, 3, 3, 7, 8, 4, 5, 6, 0. So we see 133,784,560. So given that we have this many different 7 card combinations in a 52 card deck, you can see why actually winning a specific hand combination is such a big deal. Okay? So again, putting this into your calculator, you're going to hit the menu button, probability, and then combinations, and you'll enter 52. Your comma button is on the lower left. It's right below the pi button, and then you'll enter 7. And then you'll arrow out of the parentheses and press enter and to get your number, okay? Now we want to talk about a different type of problem. Here we have different categories within this combination, okay? So we want to select a team of 10 students, 5 boys and 5 girls, from 8 boys and 12 girls, right? So of our 8 boys, we want to select 5 of them, right? We want to know the number of combinations, so that's 8 things taken 5 at a time, right? And then from our 12 girls, we want to select 5 of them. So that is 12 C5, right? And we want to multiply those two because we want girls and boys, and is indicating multiplication at this time. So we can put both of these things in our calculator. All we're going to do is hit our menu button and probability combinations, and we'll put 8, 5, arrow out, hit times, re-access that menu, and put 12, 5, hit enter, and we get that we have 44,352 different team combinations, okay? So The question may be entering your head, well, how do I know if I use a permutation or a combination? Well, really, you're asking yourself with the question, does order matter? Okay? If I'm putting people into specific slots, if I'm putting things into specific slots where order does matter, then I'm going to use permutations. If I really don't care about order, I'm going to use combinations, okay? So we've learned to solve simple counting problems. We've learned to use the fundamental counting principle to solve counting problems. We've learned to use permutations and combinations to solve counting problems. And hopefully by now you have a better idea of how to solve these counting problems, and we'll do more in class as well.